Okay, hello students. You're welcome to chapter 2, part 5 of network accession management. Discuss network accession management, and this chapter is cable testing and certification. Let's quickly go through this. Now here we're going to have the objective of this chapter will be the need for increased data rate. Why we need to increase the data rate, and why is it that we have to push due to the technology that keep coming out of twisted pair cable to even greater performance requirements and placing even greater demands on accurate testing of the cable infrastructure. So we need to see why the data rate, the need why data rate keep increasing, and the things that comes with this increased data rate. Then the EATIA 568B standard that defines the minimal cable specification for twisted pair cable categories operating over the bandwidth of over 600 megahertz and the data rate of up to 10 gigabit per second. And remember, 10 gigabit per second is called super gigabit Ethernet. So these are the two aspects we're going to look at for this chapter. Now let's quickly go on. Cable testing. The Cat 5E and Cat 6, that means category 5E and category 6 designation is simply the minimum performance measurement for cable, and the attached terminating hardware such as the ROG 45 plugs, ROG 45 jacks, and ROG 45 patch panels. So these are the minimums. So meaning for cabling, for standard cabling, for big Ethernet cabling, we use 5E and Cat 6 as our minimum performance measurement. So going anything below this, going below 5E, like you're using category 5 or category 3, it's not supported to this fast Ethernet. Okay, so today's fast Ethernet is being the minimum we can go for it is category 5, enhanced category 5, and category 6. This is the minimum performance measurement that will carry on the cable, and not just the cable, every other terminating hardware that we attach on the cable, like the ROG 45 plug and the ROG 45 jack and the patch panels. Okay, now let's quickly take a look at a full channel. A channel consists of a link and a full channel itself. Now cable tests are conducted over these two aspects. The link here, a link is the end of a wire to the other end of the wire. That's a link. Okay, a link actually link the wall plate to maybe the patch panel and eventually to the hub or switch. So if you take a look at everything that you're talking about, the full channel, but just from one end of a wire in the wall plate to the patch panel, the other end of the other wire that links to the patch panel is called a link. It's just called a link. A link is the point from one cable termination to another. So the one cable termination, you're terminating this cable at the wall plate, at this wall plate. This is a wall plate. This place is a wall plate, and then you also terminated the other end of this cable at the patch panel in the telecommunication closer. It could be your modem in your house. Okay, you're terminating this one at the patch panel, and then from here again you take from this other side of this patch panel to the hub or the switch, usually the switch nowadays. Now the whole of this is called a full channel. It's called a full channel. A full channel consists of all the links element from the hub or from the switch to the wall plate, all the way from the switch to the wall plate. Is that okay? Now let's move on quickly, because we have, okay, this is what this is showing you. This is a link. From here to here it's a link, and then the whole thing is called full channel. It's called what? Full channel. Let's move on quickly. Now this is EATIA 568B. Okay, this is the standard for our cable. You remember we said that before. So we are looking at category 5E, category 6, and category 7 cable specification. So here we're going to look at this different category, and we look at some parameters. These parameters could be in terms of which class, which bandwidth, the insertion loss. Insertion loss is called attenuation anyway. So the insertion loss or the attenuation, the near edge signal, and then we talk about the crosstalk, and then we talk about the power sum near edge crosstalk signal. All of this, we're going to look at these factors and what the role they play in the cable. So we are looking at so many parameters. You can see we itemize a lot of parameters, and we're going to be describing it. Now let's get it started. First, with the bandwidth. The first one, talk about the class. Category 5E is class D. Category 6, we've talked about this before. Category 6 is class E. Category 6A is class EA. Category 7 and 7A, they are both in class F and class FA. So that's no problem. We've talked about that. Then the bandwidth for cabling in category 5E is 100 megahertz. The bandwidth for cabling in category 6 is 250 megahertz. The bandwidth for cabling in category 6 is 500 megahertz. And then category 7 is using 600 megahertz, and up to 7A is using about 1000 megahertz. These are huge channels, big channels. Now we talk about insertion loss. Insertion loss is also known as attenuation. This insertion loss is the same thing as attenuation. They are measured in decibel. The values are measured in decibel. Okay. Now, what is the meaning of attenuation? If we say insertion loss is same as attenuation, well then what is attenuation? Attenuation is a parameter that defines the amount of loss in signal strength as it propagates down the wire. The loss, the degradation in the value of the signal as it travels in the wire, as it moves in the wire, is called attenuation. Signals as they travel in wire, they attenuate, they fade away gradually, they lose strength gradually. So as they travel, the longer distance they go, the more the attenuation, they lose their signals. Okay, now let's quickly move to the next one. The next one is called next is near edge crosstalk. So there's a loss that happens to the signal in the near edge. Okay, we're going to demonstrate that near edge crosstalk. So crosstalk emanating from wires that are close to each other or probably adjacent to each other. You know, signals, your voice signals are converted to current and they travel in wire. They don't travel in form of voice or in form of physical parameter. They travel in form of current. Your signal you're talking, you are making hello, you are making on your telephone or your network. They are all converted to electric current. And as they travel in current, you remember when current flows in wire, electromagnetic field is produced. A field is produced. So this field, when it's adjacent to another wire, it will reduce the voltage in another wire, which causes a crosstalk in these wires. Is that okay? So you can see this near air crosstalk loss is increasing from this category 6, 5E 30.1, then 39 in category 6, 39.9 in category 7. And as you go to category 7A, it gets to 62.9. So you see it increases. We're going to discuss that effect later on. Let's move on quickly. Before we go to describe or discuss PS next loss in decibel, let's quickly understand what is near air crosstalk. You see, a signal. This is one device. This is another device. Now this device transmits a signal right from here to here. You see, close to the signal there are a little bit of loss or a little bit of crosstalk. It's called near edge crosstalk. And then a little bit, and the other end, receiving end, there's also a crosstalk happening to it. Now this is a full duplex mode. This device also transmit and this device also receive. Now this crosstalk happening at the near end to the device on this part and also on this part is called the near air crosstalk. Is that okay? It's called the near air crosstalk. Now when current travels in wire, an electromagnetic field is created. Whenever current travels, because your voice is converted to current. Okay, when current travels, you do sensor attenuator later. We will talk about actuators and sensors later, how physical devices or how our physical parameters are being converted to current or voltages as they move in a wire. We'll talk about that later. Now quickly, whenever current travels in wire, electromagnetic field is created, is produced. Now this field can induce a voltage in adjacent wire resulting to crosstalk. they will induce voltage. You remember Faraday's law, right, in electromagnetic induction. So this field will induce voltage in adjacent wire that are close to the wire. You know, wires are in pair. So any adjacent wire, we'll show you how wires are adjacent to each other. So any adjacent wire, a crosstalk can result to it. Now, crosstalk is what you occasionally hear on the telephone when you can faintly hear another conversation. When you occasionally, this is not all the time. So, but occasionally, when you are talking on the phone, when you can faintly hear, you begin to hear some kind of some other signal that are not the voice signal that you are supposed to hear from your correspondent. So when your signal has faded, or you can faintly hear your signal, then you hear other things. Those things you hear, they are called the crosstalk. Crosstalk is what you occasionally hear on the telephone when you faintly hear another conversation. Now, near ear crosstalk, or what we simply call next, is called the near ear crosstalk. Is a measure of the level of crosstalk. The measure of the level of crosstalk or signal coupling within the cable. The measure of the level, because near end here we measure how much crosstalk this device is hearing. This is let's say this is a mobile phone. How much other background noise you're hearing. Okay, and also this other guy that's receiving from you, it's also how much of this is he hearing. So these are called the near end crosstalk. And this near end crosstalk, which is next, is the measure of the level of crosstalk or signal coupling within the cable. Now the measurement is called near air testing, because the receiver is more likely to pick up the crosstalk from the transmit to the receiver wire pairs at both ends. This one transmit, this one receive, this one transmit, this one receive. So from both ends, they both hearing this crosstalk. Okay, they're both hearing this crosstalk. Okay, we say this measurement is called the near air testing. If you measure this signal, this near air signal, then you're actually testing how much near air is found in this system, right? Because the receiver is more likely to pick up the crosstalk from the transmit to the receiver wire. So from the transmit to the receiver wire, the receiver will most likely pick it up. And also similarly, this transmit, the receiver on the other side will also pick up this near end. So this testing needs to be carried out in order for us to know how much of it is affecting our signal, because crosstalk is a big deal that affects our signal in cabling. Now the transmit signal level at each end are strong. So when you are transmitting, the signal level is very strong here, but when it's getting here, it's gradually faded, maybe due to crosstalk, due to attenuation, or what you call the insertion loss, and so on and so forth. So many factors affect the signal, but at the transmit side, these signals are very strong. The signal levels are very strong, and the cable is more susceptible to crosstalk at this point. So the cable can be fed with a crosstalk. Now additionally, the received signal level have been attenuated due to normal cable path loss and are significantly weaker than the transmit signal. So the signal that you transmit from here is stronger than the signal that is being received from here. The one of the factors is the path loss. There's what we call path loss. There's insertion loss. There is crosstalk. Insertion loss results from the crosstalk happening to this device or to this boat, and all these signal loss and all of this, they are measured in decibel. Okay, they are measured. A high near air crosstalk decibel value is desirable. You need a very high value of this in order to improve the transmission signal. Okay, now let's move on to the cross section of a Cat6 cable. Now every Cat6 cable, now we introduce what we call a separator. You see, the starting from Cat6 cable, we introduce what we call the separator. This separator separates these pair wires. These are the twisted pair. The twisted pair, you know, this twisted pair is like he has his own apartment. It's like he has his own apartment. This one has his own apartment. This one has his own apartment. It's like 4 flats. What you see here is like 4 flats. This pair, let's assume this are husband and wife, positive and negative pair of wires. So these ones are what? They are they are living in their own apartment. This one are now living. The reason why we are doing this, we introduce separator, is to reduce the crosstalk, to reduce the effect of crosstalk that are adjacent to each other, okay, that are angle 90 to each other. Remember, these two wires are not angle 90, they are parallel to each other. But by the time you compare to the other side, they could be 90 degree to each other. You see, here to this way could be 90 degree. So they are adjacent, and that will create a crosstalk on this end, because voltage will be induced, because field are here. As current flows in this wire, field it will be generated, field will be produced, and this field induce voltage on this other side, and every voltage that is on this other side causes what we call the crosstalk. Every voltage that is induced here as a result of the electromagnetic field here, it causes what we call the crosstalk on this other side. So to avert this, we introduce what we call separators. The separators inhibit the voltage to be induced here, prevent voltage being induced here, and that now brings about improvement in the use of the wire. That brings a total improvement in the use of these cables for networking. Crosstalk is more problematic at a higher data rate. The higher the data, the more the crosstalk. So we need to do something. That's why we introduce a separator to help us improve this. A higher data rate could be 1 gigabit. That's too much. That's 1000 megabit per second, 1 gigabit per second, or 10 gigabit per second, which is 10,000 megabit per second. So high data rates are of these categories. Category 6 cable has a built-in separator. We've already explained this, to help minimize the crosstalk among wires pairs as shown. Among wire pairs, to minimize crosstalk. This is very important. The separator is used to keep each wire pair at a minimal distance from other wire pairs. Separator helps to keep them at minimum distance from other wire pairs. This addition reduces crosstalk and higher frequency, and this level provides improved signal bandwidth, and therefore it will support faster data rate. So this one will support faster data rate because it will suppress the crosstalk coming from this kind of cabling. It will suppress the crosstalk to happen on near air crosstalk happening to these cables, and hence we improve the bandwidth. Therefore, that will result to higher capability of data transfer rate. Okay, now let's move on quickly to the next one. Now we are back to this, explaining this from the concept that we have left it, from where we've left it. Now we come to PS next, the power sum. Power sum next is the enhanced twisted pair cable. Every enhanced twisted pair cable must meet four pair nest requirement. Every enhanced twisted pair cable must use the whole 4 wire pairs, which is called the power sum. When we are discussing one pair, then we just talk about the nest loss. But when we are talking about all 4 pairs lost, then we are talking about what we call the power sum, the PS nest. So when we are talking for, like just now, if I'm talking about this nest, this near end crosstalk, if I'm talking about the crosstalk only at this level, then it's just the nest. But if I have to talk about the nest here, the nest here, the nest here, the nest here, then it will all become a sum of all 4 wire pairs, and this is called the PS nest, which is the power sum nest, right? Okay, now let's move ahead. So we get that. So when you test all 4, you are doing the PS nest testing. So basically, power sum testing measures the total crosstalk of all the cables, all the cable pairs. This pair, this pair, this pair. Let's take a look at all the pair. This pair, this pair, this pair, this pair. So when you are testing all of them, then you are doing a PS nest. When you're testing all the power in all of them, you are doing a PS nest. And then this test ensures that the cable can carry data traffic on all 4 pairs at the same time with minimal interference. Okay, this test that you carry out will ensure that the cable can carry data traffic on all 4 pairs at the same time with minimum interference. Okay, now let's go on quickly. Then we go to another parameters that we use in the specification of these different categories of cables. Now another parameters that is used is the ACRO, attenuation to crosstalk ratio. This is called the attenuation to crosstalk ratio. Manufacturers combine these two measurements of attenuation and crosstalk on a data sheet and list this combined measurement as attenuation to crosstalk ratio. So they combine these two. Attenuation is a parameter in networking that should be handled, and crosstalk is also another parameter. But we can bring both of them together, and when we bring both of them together in a ratio, this over this, attenuation over crosstalk, when we divide the values of attenuation by the crosstalk, we get a new parameter called the attenuation to crosstalk ratio. Is that okay? We get this value for attenuation to crosstalk ratio. Okay, now this attenuation, the larger the attenuation to crosstalk ratio shows that the cable has a greater data capacity. So if you want a greater capacity, then we have to find a larger attenuation to crosstalk ratio in decibel. The bigger the values, the more the data and the cable can handle the data in the channel. Now, for example, if you have category 5, this is 6.1. Category 5 is 6.1. Category 6 is 80.6. It's a huge value increase from 6.1 to 80.6, a huge value increase in category 6. So the larger this attenuation to crosstalk ratio, then the more capability the cable has to handle data at a faster rate. Okay, so you can see in category 7 and 7A, the value has jumped to 42.1 up to 46.1. So this is a huge value. The bigger this value, the better the channel, or the better the cable for the bigger and the better and the greater the bandwidth that is used. Now let's go to another one, which we call the PS, attenuation to crosstalk ratio. PS is the power sum, meaning you are doing for all the 4 wire pairs. The power sum attenuation to crosstalk ratio uses all the 4 wire pairs to obtain the measure of the attenuation crosstalk ratio. If you do for 1 pair, then you are just doing the attenuation to crosstalk ratio. If you do for all the 4 wire pairs, then you have a PS sum. You have what we call the PS sum. So the PS sum does the work for all the 4 wire pairs, right? You find all the attenuation to crosstalk ratio in all the 4 wires. Now this is a measurement of the difference between the PS nest and attenuation. So the measurement of the difference between the PS nest and attenuation. PS nest minus attenuation. Attenuation, remember, is the insertion loss. So when you are saying the PS nest, the one we've done before, the PS nest minus the attenuation, you will be getting this PS sum, PS ACRO, which is the attenuation to crosstalk ratio, the power sum attenuation to crosstalk ratio. So in order to find this, is just to find the difference between the PS nest and the attenuation. Then you get a new value, which is called the PS ACRO. This difference is measured in decibel, and remember all these power ratios are measured in decibel, okay? And the higher PSA ACRO, that's the power sum attenuation to crosstalk ratio, the higher the value in decibel, then the more or the better the performance of the cable. Now let's move to the next one. Another one called the equal level first. First is far end crosstalk. So EL first means equal level far end crosstalk. Okay, this is another parameter we carry out in network engineering. Okay, this is another parameter we carry out in network engineering, computer science and network engineering. So what we do is that we calculate, or this calculation obtained by subtracting. If you want to get this value, you will get this by subtracting the attenuation value from the far end crosstalk. So to get this value, you first of all get the values of the far end crosstalk. When you get the values of the far end crosstalk, you have to subtract the attenuation values from this far end crosstalk. When you do that, then you get what we call the equal level far end crosstalk. Is that okay? Now a poor EL fix can result in poor data loss, right? Can result in data loss. Poor ELFX, it resulted to data loss. High LFS value in decibel indicates a signal at the far end of the cable are larger than the crosstalk measured in the far end. So when you have a far LFX that's equal level, far end crosstalk, when you have this value, bigger of this value, shows that you have a better data at the received end, because your data received is greater than the crosstalk in the signal, hence it's a better value. But if you have a poor signal outing from here, it shows that there is a not good capability or good transmission happening at the cable. Okay, a larger phase is desirable. Of course. A poor phase can result in data loss. Now let's go to the next one. Then we have what we call PSL first. PSL first is a power sum. Anytime you see PS is power sum. Power sum is to do for all the pairs, all the 4-wire pairs. When you do only L first, you are only doing for the pair, one pair of the cable. When you now do PSL first, you are doing for all the 4-wire pairs. Okay, power sum L first. It uses all the 4-wire pairs to obtain the combined L first performance measurement. Okay, so the bigger the value, the better the data transfer rate in the cable. Okay, now let's move on to the next one. Return loss. Return loss provide a measure of the ratio of power transmitted into a cable to the amount of power returned or reflected. You know, when we transmit data in a cable, some of them will be reflected. This is a norm. Not everything you transmit that will be received exactly. Some of them will be reflected due to the cable factor. This is cable factor. Some of them will be reflected. Okay, so no matter how you try to improve the system, some of them will be reflected. Now, return loss is the measure of the ratio of the power transmitted into a cable to the amount of power returned or reflected. So that tells us about return loss. Now let's still take a look at about this return loss. The signal reflected is due to the impedance changes in the cable link. There are impedance changes in the cable. Remember, every cable has a resistor. Not only a resistor, has also capacitive in the system, has also inductor in the system. So when you have a combination of resistors and capacitors, or resistor and inductor, or the combination of all three, the combination of resistor, capacitor and inductance, then this will result to what we call impedance. So this impedance, just the same way the resistor resists the flow of current, impedance resists the flow of current. Remember, all your signals are converted to current as they flow in a wire. All your signals are converted to current as they flow in a wire. So this impedance is a complex resistor. Impedance is a complex resistor which includes not only the value of the resistance from the resistor, it also includes the value of resistance from the inductance, which we call the inductance, the value of the resistance in inductor called the inductance, the value of the resistance in the capacitor called the capacitance. So both the capacitance and the inductance and the resistance all combined create what we call the impedance. Now this impedance result to loss, result to the reason why signals are reflected. The result, all this one creates a ability and a factor that result to signals being reflected. Now when these signals are reflected, then that result to what we call return loss, because the amount of power transmitted and the amount of power that is being reflected, the difference in this is what we call the return loss. Now the signal reflected is due to impedance changes in the cable link, and the impedance changes contributed to the cable loss itself, the link and the cable itself. Okay, each individual cable and the link itself. Now cables are not perfect. Of course they are not perfect. Even human beings are not perfect, let alone cables. Okay, let alone what the human being created. Okay, so cables are not perfect, so there will always be some reflection. There will always be some reflection. I've explained the reason why reflections happens in cable. Reflection happens because of the resistance of the wire, because of the inductance in the system, because of the capacitance in the system. So these impedance all combined create what we call the impedance, which is a complex resistance. Now this complex resistance called impedance result to reflection in cabling, and this reflection reduces the strength of the signal. Let's move on quickly. Now we are jumping to the propagation delay because others are just insignificant. Propagation delay is the measure of the amount of time it takes for a signal to propagate from one end of the cable to the other. From one end of a cable, the amount of time taken, for the signal to propagate from one end of the cable to another end of the cable. That time is called propagation delay. This delay of signal is affected by the nominal velocity of propagation of the cable. So we're going to talk what is nominal velocity of propagation of cable. We're going to talk, since we say this delay, the propagation delay is affected by nominal velocity of propagation, then what is nominal velocity of propagation? Now, nominal velocity of propagation is just some percentage of velocity of light. It's just some percentage of velocity of light that is being reflected. Okay, it's just some percentage of velocity of light that is being reflected. You know, the velocity of light that is moving in the velocity of light, or the velocity of the signal that is moving in the cable, what percentage of it is reflected? What is the speed of this percentage of it that is reflected? What is the percentage of this light that is reflected? So when we calculate this percentage of light that's reflected, then compare it to the signal that's in the whole cable, then we call this nominal velocity of propagation. So simply put, nominal velocity of propagation is just some percentage of velocity of light, and this is dependent on the type of cabling that is being used. Enhanced cabling like 6 or 6A has a reduced nominal velocity of propagation compared to cable 5 and 5E. Now typical delay values for Cat5, Cat5E UTP cable is about 5.7 nanoseconds per meter. Okay, so in 1 meter we have only 5.7 nanosecond. Nanosecond means times 5.7 times 10 to the power of -9, which means 0.00000000057. So this is the speed. This is the delay, amount of delay that happens. Is really infinitesimal in many cases. Is very infinitesimal. The ERTR, but we still have to learn it because this is engineering. We don't leave anything untouched. The ERTR specifications allow for 548 nanoseconds for the maximum 100 meter run for Cat5 and Cat5E. That's the maximum you get. And then maximum you can get nanosecond. We're talking about nanoseconds. 548. It's not 548 seconds. 548 nanoseconds. That's the maximum you can get for 100 meter cable. For 100 meter cable, this is the maximum delay time, propagation time that you can have. If it's more than this, then there's a problem. Therefore, Cat6, category 6, the maximum is 546. It's reduced here, 546. So mini Cat6 is an improvement of the whole 100 meter cable. Is that okay? For the delay time, the propagation time. Okay, now let's move to the next one. What we call the delay skew. This is a new parameter that has been introduced in engineering. Delay skew is a new parameter. It's an enhanced performance specification of Cat5E twisted pair cable, and it includes new specification for testing. We use this one to test our cables now to see that the enhancement in cabling. This delay skew is used just to show how much improvement we've done so far. Delay skew is just the measure of the difference in the arrival time between the fastest and the slowest signal in UTP wire pair. You know, the wires are in pair, so the arrival time between the fastest and the slowest, that difference in the time in the fastest and the slowest is called the delay skew. It's called the delay skew. Okay, now let's move on. This delay skew is is critical in high-speed data transmission. Okay, but for low speed, like all the other ones we've been doing before, this may not be an issue. But for high-speed data transmission, this delay skew is very critical, right? It's critical that the data on the wire pair arrive at the other end at the same time. We need to establish that the data are arriving at the same time. There should be no one arrival before the other one, because when one arrive at the at one end before the other one, then we have what we call the delay skew, and we have to measure the delay skew and see how we can improve this to reduce data arriving before each other. One data in one wire of the pair arriving before the other. Now, if the wire length of different wire pairs are significantly different, maybe one is longer than the other, then the data on one wire will take longer to propagate. This is very obvious. This is significant. If one wire is longer than the other one, then it will take a longer time for that longer wire to deliver the data. Okay, so hence arriving at the receiver at different time and potentially creating a distortion of the data. So that's why we want the wire pair to be of equal length. If they are of different length sizes, then data will obviously arrive at different time, and then there will be what we call the delay skew. Delay skew will be very paramount. So in order to reduce this, we ensure that the pair of wires are of the same length. Is that okay? Now let's move on quickly. Power sum measurement. Now, how do we carry out the power sum? How do we measure the power sum? We'll be talking about the power sum. For every parameter we talk about the power sum, because the power sum considers all four pair wires, right? It considers all four pair wires. So how do we carry out this measurement? The power sum measurements are critical for high-speed data communication over UTP cables. Now, it has also been shown that twisted pair can handle gigabit data rates. Twisted pair can handle gigabit data rates over a long distance, up to 100 meters, not only optical fiber. Twisted pair UTP cables can handle this, not only optical. We're going to come to the chapter of optical fiber, which is a super emerging way of transmitting data. However, the gigabit data rate capability of twisted pair requires the use of all four pair wires in the cable, with each pair handling about, let's say if you are talking about 1000 megabit per second, each pair of wire will handle 250 megabit per second of the data. So if you put the four together, you say 4 times 250, which is being handled by one pair of wire, will give us the 1000 megabit per second, which is equivalent to 1 gigabit per second, Is that okay? Hence, the need to obtain the combined performance measurement of all four pairs is very desirable, because this will help us to increase the high data transfer rate. This will increase the data transfer rate in our channel. Now let's move on to, let's take a look at all the things. These are terminologies that we have used. We've talked about the link, we talked about the full channel, the attenuation, the near Air Crosstalk, we talked about crosstalk itself, we talked about power sum nest, we talked about equal level nest. So these are some of the things we talk about: PSEL first, ACRO, the attenuation, crosstalk rate to crosstalk ratio, power sum to attenuation, crosstalk ratio, return loss, propagation delay, nominal velocity of propagation, delay skew. All of this we've talked about, and thank you. And this is the end of our class for today, and you're welcome to the next section, which is chapter 2, part 6. Thank you.